Okay, so yeah, let's talk about Rust and what it is and why we're making it. So it's a new systems programming language. Actually, so much of my talk, I wish I had the time to revise it entirely based on Bjarne's, because so much overlap is there. So we need to have fast code for systems programming, and we want to have a good FFI interface to interface with native services. You want to have low-level control, things like data layout. But also, we've got decades of PL knowledge to draw upon. So we want to mix in all these classic ideas, drawing from the best of breed stuff, stuff from C++ like RAII, but also things from the ML and Haskell and et cetera communities with generics and F-bounded polymorphism, et cetera, pattern matching, all that great stuff. But perhaps most importantly, the most exciting thing about Rust is the focus on safety. And that for us means not just being memory safe, in terms of no seg faults, no pointer dereferences, or garbage pointer dereferences, but also a new condition for safety, which is to be data erase free, which is pretty awesome. And there's a great blog post about this topic called Fearless Concurrency. So yeah, all the stuff you need to hack on Rust yourself is at this website. So you could all go there right now and download the Rust compiler and start running your computer right now. And of course, you're all doing that, I can see. But perhaps more importantly, the playpen is something that you can get to. I might not be able to get to it, actually. But this is something that you can actually visit and run yourself in the browser. And it goes to a dedicated service online. So these slides, actually, every piece of code that I have on here has links to the playpen. So we're going to see some demos to get you all geared up. These are like 3 little tasty tidbits. So the first thing, zero cost abstraction. We heard Bjarne say that over and over again. It's a huge thing for us too, but not to compromise safety. That's the first and foremost thing. But still, zero cost abstraction. So this is some pretty high level code here where we're doing some iteration over an input vector, and we're doing a filter as we go, and then summing. And this compiles into this assembly code. This is really tight assembly code considering how relatively high level that code was. And in fact, if you want to get even more high level, you could have written the code like this, and it compiles into the same assembly code. And this is due to a mix of stuff between both relying on LLVM to do great optimizations, but also, question?
What's I between the types?
That's a closure. That's our syntax for closures, which we may or may not get to in this talk. We'll find out. But that's our syntax for, a lambda expression is the I within the bars. So, yeah. But it's not just LLVM that we're relying on here. It's also that the iterator abstraction we use allows us to do things like not have bounds checks during the actual iteration itself. But also, we have memory safety. And this is an example I like because this isn't an example that everyone necessarily thinks of. In particular, this is a bug that plagues even safe languages like Java. Namely, you may have heard of concurrent modification exception when you try to modify a collection while you're iterating over it. Rust doesn't have this. So in particular, this example is one where in C++, if you try to modify a vector while you're iterating over it, that's a bug. As in, it might reallocate the backing store for the vector, but the iterator doesn't know that. And so you've just invalidated the iterator, but it doesn't detect that, and so you just get garbage. But we detect it and tell you at statically compile time, no, not allowed. And here's why. Yep.
When you said you optimize the iterators, does the compiler know about the iterator to optimize it?
No, that's something that's the iterator constructs a library, so there is some special code in there where the iterator is itself taking advantage. There's a tight coupling between the vector representation and the iterator that it yields when you ask for it.
Great, thanks.
Okay, and finally, the other point I wanted to make was about concurrency. I'm trying to get to a lot of slides here. Oh no. Oh, okay, that makes sense, actually. I tried to get to something that I couldn't get to. Oh no, this is very bad. How do I get back? Sorry, I'm using a hacked version of my Chrome for Mozilla, so it doesn't show up, for Firefox, so it doesn't show the URL bar, but unfortunately, it doesn't show the URL bar, ever. So we need a presentation mode. So anyway, this is an example of fork join concurrency. So this is really slick because we have some data that's owned by the local stack frame, namely or somebody. It's owned by somebody. It's not owned by the local stack frame. It's something we've borrowed. But the point is that we can split the input array into 4 chunks, hand them off to threads, and have them process those things concurrently, and then, but just passing off pointers. We're not making copies of the data, and then we like do our processing and get a result back. Of course, you wouldn't typically do this for something like Max. That's kind of stupid, but this is just illustrative. There is a caveat, which maybe we'll get to. We'll see. So, okay, but why Rust? Why, in particular, why is Mozilla doing this? And the simple answer is because it's the only way we see it to be competitive. We don't have enough of a workforce to, especially with a volunteer work base and so on, that we need to compete. But C and C++, it impedes our productivity too much. So, for fast experimentation with new ideas into the future of what web browsers can do, we want a different system for that. So, in particular, we have this thing called Servo. It's a separate project. It's a browser implementation research platform. It's written in Rust. This code's open source, et cetera. And so we're using that to do experiments like things like doing painting in parallel, or doing parallel layout, or parallel CSS selection matching, various experimental things. So one more thing, a note about goals here, because you might think that we're all totally focused on static safety and whatnot, but in fact, Rust is more than happy to use dynamic checks to ensure soundness when appropriate. Because what is soundness anyway? It's not okay to have a seg fault, in our opinion, but a clean shutdown of the system when you have some internal invariant broken, that's actually okay in our book. Bugs, if you can recover from a bug in some way and actually shut down the system cleanly, that's not the same kind of risk that a seg fault represents. So we actually have forms for doing that kind of clean shutdown and then doing proper unwinding of the stack, much like what Bjorn was talking about today with using destructors and having exceptions and properly cleaning up after them. But we do static analysis where we can. So how are we going to get this? How do we get this done? What's the main pieces to this? Again, I wish that I'd redone this in terms of Bjorn's talk. So move semantics is a huge, huge part of our story. And it's basically something that's built into the language from the ground up. Because it gives us much just direct control and direct expression of what the resources are that you're representing in your program. And we have this notion of borrowing, which gives us back references. We'll be talking about that later. And then finally, we have lifetimes, which is our way of actually putting constraints on the references in the system. So you may have noticed during Bjorn's talk, somebody mentioned about how, if this is after the timeout, that they were mentioning, wait a minute, you're giving back a reference there, and you have to ensure that that doesn't outlive the thing it's referencing into. And he was like, yep, you do. But, okay, that was the programmer's job to ensure that there. In Rust, you can actually encode it, and it's statically checked. So this is a demo of move semantics. I'm not going to belabor it too much, but the main idea is that you have this vector you create, and then you actually can modify it, and then when you make a call, like this sum call over here, you actually are moving that resource to that other call site, and thus it can't access it after that point. And likewise, if you then take a vec as an argument and you don't move it somewhere else, then at the end of your scope, it's cleaned up, just like in C++'s model of resources. Okay, not everything is moved. It doesn't make sense to move an integer. You can just freely copy those. They don't represent the resources. So there's this notion of things that are like resources and thus can't be copied like that, and things that are not resources. And there's the interface called copy that we use to represent this. And then there's a selection of errors that I have illustrating here, but I don't want to take too much time on it. The point is that we catch you when you make mistakes trying to access things that moved. You can check out the slides yourself. The big problem here, of course, is that if you just had a language only with move semantics, it would be unusable. This is not a you can't just rely on move semantics because you need to reuse stuff from time to time. So this is where you need pointers. And the answer then is how do we bring pointers back? And the way we do it is we reuse the syntax of C's address of operator, but it's conceptually a bit of a different notion. It's not that we are taking the address of something, but I prefer to think of it more abstractly, that we're borrowing a reference to that data and then handing that out. So that's what a borrow looks like. So, okay, we have borrows. Great, everything's solved, right? No. No. You see that we're bringing back all the same problems we had before with it, because the reason that bugs happen is because, well, a reason that you can't just statically detect all the bugs in the world is largely because of aliasing. It becomes too hard to analyze code. And borrows would reintroduce aliasing. So what do? We restrict it. And the analogy here that I've come to appreciate is when you're doing concurrent systems programming, there's the notion of, you can use a notion of abstraction called a reader-writer lock, where you either have many readers at once that only have read-only access, or you have one writer that has read-write access and it's exclusive access to the thing. And we have a similar model in Rust. So this is encoding the type system statically. There's types T. There's things that correspond to the readers that are ampersand T. And then there's things that correspond to writers that have exclusive access, and that's ampersand mute T. So here's some concrete examples of those types again. So if you're doing a read of data, then you take an ampersand vec, and that'll let you get read access to the data. But you can't, for example, move strings out of that vector because you can't do that here because the vector, you only have read-only access to it. You can't do things like change its size. You can only just take references into it. Or you could modify the vector. So here we can actually take an ampersand mute vec and then push things onto it. And finally, you can have something where you transfer ownership of the vector. And this actually consumes the vector by iterating over it. And this code is kind of funny. What it's doing is it says, oh, I take the vector, I do a for loop, but then if I see anything at all, I take the object, which now I've actually moved out. Compare this bottom example to the top one. The top one, I'm not allowed to move the first element of the vector out of it. But in the bottom, that's the only thing that's happening is moves of each element out of the vector because it's being consumed on that very first line. Okay, this is what calls look like. It should be pretty intuitive based on what I showed before in terms of there's ampersand v for taking a read-only borrow that's aliasable, ampersand mute v for the read-write one, and then no ampersand at all for when you're going to transfer it directly. I don't know if I really want to talk too much about this. So the issue here is that I haven't gotten too many questions yet, and there are a lot of slides here. So I'd like to get some sort of input from the audience about where we should go. So, okay, lifetimes. Oh, shoot, that means we do need to talk about this. Okay, back to this then. So I was talking before about borrowing, and here's some concrete example. When you borrow something, there's a definite extent that we represent statically within the compiler that corresponds roughly to lexical scope. It's kind of like lexical scope, except there's some finer grained things that don't correspond to explicit variables sometimes. But here I've made it very explicit by explicitly binding all the intermediate expressions for the borrows that happen. So you can see that R2 is being borrowed at the very bottom there, and its scope is strictly less than R1's, and then those are each less than V2 and V1. Okay. And then when you make a call like foo, each call to foo has to choose the appropriate scope to plug in for, yes?
Can you explain the exclamation mark?
Absolutely, good question. We have macros, sorry. So I love macros, so I actually say that somewhat facetiously, but Bjarne really seemed like he had something against them. I guess if we were awesome, we would figure out a way to do... True. We have hygienic macros. That's sort of. We try really hard. We'll probably get even better later, but the point is they're mostly hygienic. And so for constructs, the way that instead of having variable arity constructors, like in C++, to do things like a vec construction, instead we have a vec macro that constructs an empty vector and then pushes each element onto it. And then that's succinctly summarized in this vec bang, or vec exclamation point. I'm going to probably pronounce it bang for the rest of the talk. Sorry. So likewise, the println down here, println bang, that's another macro. And it's a lot like C's printf function, except it's a macro, and thus it can check that your arguments that you give actually correspond to the template string, and it statically checks this. Yes. Oh, you do it, right? Okay.
This way we can actually hear the recording.
All right. So why do you need a bang to invoke a macro?
Some people like to get immediate visual feedback that a macro is there, and they believe that it's necessary for humans and/or for tools to tell you that there's a macro here. I'm a scheme person, so I don't understand this logic, but I accept it.
It's not a question. I think I think there's also the thing that the parser knows about macro, so it consumes like everything. So
I think
you
that-
have that separated. I'm not sure. I think
I
that's the
I
reason.
believe that problem could be solved.
Oh,
I could be, maybe not. That's an interesting point. It depends on how you deal with name resolution. If you interleave name resolution and parsing, then you should be able to deal with that. But we don't currently do that. So that's actually a good point. I don't think we could do it with Rust as of today or yesterday, but I think that Rust in the future would be able to deal with that detail.
Okay. Thanks.
Yeah, okay, so that's great. The bangs are the macros. But like the other thing here that's new syntax is the input to the foo function here is not just taking a reference, but it has a reference with explicit lifetime on it, that lifetime tick A. So it says this is a reference that lives for at least as long as tick A, whatever tick A is. And what is tick A? The compiler has to figure that out. We don't currently have a way, well, we typically don't try to explicitly instantiate the tick A's here. Instead, that we let the compiler do it. So, okay, the main point here is that we have a borrow checking system that checks for errors here in terms of your use of these lifetimes. So here, v1 got moved by the consume call, and there's still this outstanding reference to r1, and if you attempt to then call foo with r1, the compiler checks this and catches you and says, no, you can't do that. And it gives you a precise error message saying, you can't move out of, who's to blame here? Is it the call to foo or is it the call to consume? There's not enough information to actually, tick one. So the compiler says, oh, you probably didn't mean to move v1 out here because you still are going to read from it potentially down here in this call to foo. But the point is, we tell you about both points, and so you can figure it out. Okay? Now, okay, this is clearly a case where this was, buggy program. The system we have is naive. We have to admit this. It's based on lexical scope, and so even if there is no call to read after the call to consume, I want you to compare these two slides. So I had a call to foo, and that was definitely wrong. But even if I get rid of the call to foo, the current compilation model, it still treats that as an error. It still says, oh, R1 lives this long, and therefore something's wrong. This is going to go away in the future, we are almost certain. As in, we'll be able to compile this code in the future.
Could you explicitly unset a variable to avoid that?
Not with our current model of scopes. No, because that would be equivalent, for example, to just moving R1 somewhere else, sort of. But our current model for how our scope's represented doesn't handle that. But I think the answer here isn't to put it on the user. The answer is to make the compiler smarter. We can make the compiler smarter about how we represent these scopes, or regions as we sometimes call them. Okay? All right. So the main thing I want to get across here is that even though I said these are lexical scopes, they are actually non-trivial. The computation involved here and the analysis involved is not just a simple matter of doing a trivial analysis of lexical scope of variables. In particular, in this example, how long should the borrow that I have highlighted with the letter A there, how long should that last? If you read over this code, you can see that R1 is only used in the call to foo, and so it doesn't need to last very long at all. It can last just for as long as R1 does. It doesn't have the borrow, for that borrow of V1, where it says A, it doesn't need to live longer than that. So that could be a very short borrow. But compare these two slides. If I change down there so it returns R1 and binds it up to R2, now that borrow needs to live much, much longer. It needs to actually live long enough to deal with the read of R2 as well at the bottom. So that basically means you're going to have the scope of the borrow be effectively as long as V1. So not trivial.
Wait, which scope are you talking about computing?
So I'm talking about figuring out, so there's that A there.
That's what you're figuring.
Yeah, we need to figure out how long that borrow lasts. Because in particular, imagine if we added a mutation of the vector V, where that comment is. On this piece of code, you could freely mutate V. If we had internet, I'd go and show you. But you can freely mutate V, and it's not a problem. The borrow can be very short. But in this version of the code, now I pass that borrow, and it gets down to R2. R2 lives past where that comment is, and ends up being read. Yes, or I guess you.
So are the scopes always nested? All the examples that you've shown, there's always nest.
Currently, they follow a tree structure. Yeah, there's a strict nesting. I don't think that may not be the case in the future.
you do have side effects in your language, yeah?
Side effects?
Yeah.
Absolutely.
So how does it play if I let the reference escape to a global scope?
Yeah, the compiler will not let you do that unless you give it, unless the bar, there's situations where here the stack, this v1 is stack out, it's owned by this local stack frame, and so you wouldn't be able to actually let the borrow escape. It's be something where it would, there's an example in a slide later of this, but basically if you have something that's owned by the local stack frame, you wouldn't be allowed to let the borrow escape that far. It's going to be restricted to this function call.
Does this mean that nothing can actually escape to a global scope?
No, that's not true. But things you've allocated on the stack frame can't escape the local. Borrows of things on the stack frame can't escape the global scope. But for example, if there was some static data and I borrowed a pointer to that, that can escape to a global scope.
And how you define if some data is static or not?
Well, if it's statically allocated, then it's static. And there's actually a special lifetime tick static that represents this.
So on a global scope could be only something which is statically allocated, which means that it originally wasn't the global scope.
Yes, I mean in practice the reality here is that you wouldn't try to move things, and we don't move things, we don't move references like that into the global scope that often, except for when they're static data, because it doesn't make sense in terms of having independent threads that might, one might die at any point, and so moving it to a global variable, there's no better thing than to put it in global scope, modulo GC stuff. But we don't have a GC, so that's yet. Oh, sorry. Yeah, it's something where the place where this really comes up is instead not when you have a global scope, but rather if there's some function lower in your stack frame, like very deep, like if the main entry point, if that allocates an arena of stuff that you can dynamically allocate into, and that's owned by that, if you're pushing onto the stack like this, and the guy at the very bottom actually owns an arena that he can allocate into, that's a case where now you can start having borrows into things in the arena and put those references pretty much anywhere as long as it doesn't outlive your main function. So that's sort of like a global scope, since it's a lifetime of your program. And that we can actually encode. We can encode that. You haven't seen enough yet to see how, but we can do that.
That sounds like it requires whole program analysis.
No, it requires annotating your functions so that to explicitly annotate that this lifetime is being passed in and then flows out, essentially.
Does that mean that there's no heap? You don't heap allocate things?
It depends on what you mean by heap. We definitely heap allocate like malloc free,
Okay.
but we don't have a GC heap
Okay.
yet. Shh.
Yeah, what does the quote A stands for?
Yeah, the quote A, that's an example of a lifetime. So that's the syntax quote A is our explicit notation for a lifetime. And so that first foo of angle brackets tick A, that means I am parametric over a lifetime. I am, for any tick A, for any scope that someone might choose, so the calls to foo, there's two calls to foo here, and each one can choose an independent lifetime. That's the crucial thing about why this code right now works, in the sense that that first call to foo R1 can use a very short lifetime that instantiate for the tick A. But then the call at the very bottom, foo R2, is almost certainly going to choose an entirely different lifetime. It's certainly a longer one.
Okay. Do you have true virtual dispatch in your language?
True what?
Virtual dispatch.
Virtual dispatch, absolutely, yes.
Do you have polymorphism?
Yes.
Do you have lifetime polymorphism, or how?
Yes. We don't have virtual dispatch over, so you can't have a method on a virtually dispatched method that itself is type parametric. We don't have that, but we do have lifetime parametricity even for virtual methods, because they are erased to compile time. They don't have a runtime representation. They are solely for aiding the compiler and doing this analysis to determine that you've safely, all of your accesses are safe.
There's a queue of questions, one in the corner there.
So is the lifetime annotation necessary, or can the compiler infer it?
The lifetime, so we only do we don't do global type analysis, don't do global type inference, so the lifetime annotation is necessary because we're trying to avoid that. And I don't know how it would work to try to infer the lifetimes. It's not clear to me what the right way to do that would be in the first place.
Okay, cool.
It seems like a hard problem.
Thanks.
So that was my question. But then I heard you have like elision, but I don't know how. That
Yes, that's another.
works.
That's you know, we might get there.
But, okay. Could you briefly explain that or how that works?
Yeah, you know what? We might as well just move there. Sure, we'll go straight to elision, and then we'll come back. So elision. Yeah, the basic idea here is that, you know, yeah, these tick A's and tick B's are ugly. So yeah, this was some example code where you're taking in lifetimes, and some of these examples are actually taking in multiple lifetimes because there's independent references that might have independent, their data they point to might actually, one might die before the other. And so this is the very explicit form where you've actually made every lifetime for every reference explicit, but you can actually, the language, we allow you to actually elide lifetimes. And basically the rule is if it's obvious what you meant, then you can elide it. And unfortunately, I don't think I have an example right now of a case. There's also the case where you're returning a lifetime. So if you take this first function up here, this print1, if it returned a reference, even that could be elided. Because if you only take in one reference, then it's clear that the only sane thing you could do if you return a reference is to use the same lifetime for that reference. That's not 100% true. There's another sane option, but this is the best choice.
Yeah, so on the prior slide, it was.
Yeah, I can go back.
Yeah, go back real quick.
Up here.
Oh, right. How much program analysis do you need to do you only need one layer down? The compiler doesn't have to like follow the chain of lifetime analyses from one function to the next to the next.
It's essentially function local.
Function local.
There is one thing. We do have closures in the language, and so those don't have explicit types on them. So the analysis does need to have if you have a closure expression in a function, then it does have to dive into that. So that's basically part of the compilation unit, and it has to infer things there. But yeah, it's.
So related question. So how do you deal with virtual dispatch, because you don't have the bodies, right, of the functions? So what do you do then?
The way we deal with virtual dispatch is the signatures are explicit. I'm not sure if I understand the question, maybe.
Okay.
But we don't infer the signature for a function, for like a top-level function or a method.
Okay. And the second question is, do you have bounds on lifetimes?
Yes. You can say, for example, this lifetime must outlive this other lifetime.
So, and then you have a lattice ordering on
Yeah.
lifetimes?
Yes,
Can you
sort
show
of.
it? Can you show it?
No, I don't have a slide of it, if that's
okay.
what you mean.
Yeah.
But basically, static is the oldest one.
Right.
It's this sort of obvious, semi-obvious thing.
So is it like a linear thing?
I don't think I'd call it linear because you might have, there's unrelated lifetimes.
Okay. Okay. Thanks.
How difficult have you found it in practice for developers to get their head around this?
That's a great question. It's interesting. We are still working on pedagogy here. For example, there's an active debate about whether in teaching this, should you show the lifetimes explicitly from the outset, or should you leave them out and then show them later? My impression so far is that people get it eventually, but the harder part, I think, is they first have to get the ownership model. Once they sort of get that and understand that things are going to automatically be deallocated, because we're talking about some programmers here where it's like Ruby programmers who aren't used to a C++ style, RAII, you allocate the thing here and it's deallocated at the end of the scope. They're not necessarily used to that. And so once they sort of understand that piece of it, then the lifetime part kind of flows from it, sort of.
Can you say some more about the people who take up your language you were talking about? Are they employees of the company or hobby programmers or what?
We have a fantastic volunteer community, actually. I've been amazed by how many non-Mozilla, like people who don't care about Firefox, are jumping onto Rust. And this is another Bjorn reference. So Bjorn mentioned how C++ doesn't have a central community. We do. Like, we've got a great system in terms of having chat rooms and a really active user base and people actively contributing the compiler. The compiler is written in Rust, which means it's super awesome in terms of being able to hack in a compiler in this sound language, but it's still doing native code generation and whatnot. I mean, LLVM is doing most of the hard work there, to be fair. So the point is that we have an awesome community. It's not just Mozilla. It's people from all over the place. Python programmers, a lot of Rubyists for some reason that I don't quite understand. I got the impression that some Rubyists basically realized that they needed, they said, oh, I need to make some component native. And they said, well, I could do it in C, but I'm scared of C. and then they found Rust, and they figured out how to hook into Rust because we've got a pretty good FFI story, and that led to them, being able to actually make Rust plugins for Ruby.
So speaking of the FFI story, could you say more words about it?
About which?
About FFI.
The basic story there is that we have one, and if it's so, it basically lets you express. Right now, it's essentially just lets you call into things with a C calling convention. Like we have the Rust calling convention and the C calling convention, and you declare what kind of thing you're working on, and you can basically express most C types. The one thing we're missing is union, like actual union types. We don't have a good story for handling them directly in our FFI right now. You sort of have to just know what the representation the compiler is going to use, unfortunately, right now. But other than that, you can define structs. We didn't see any struct definitions yet, but we have a struct syntax, and basically you just annotate it saying this needs to get the C representation. There's an annotation system where you can say this struct needs to have the C style layout because I'm going to be using it and passing pointers into it into C code, for example.
So how does this work with additional safety measures like ownerships?
Yeah, you need to be, that's the other piece of it. So the other thing I haven't mentioned yet is that, sure, this is a safe language, but it's also a systems programming language. So how do you, make those two things mesh? And the answer is that I'm going to focus mostly on the safe language, but there is actually a superset of Rust that includes the unsafe portions of it. So what we have is a construct called unsafe, where you can actually bound a piece of code with an expression block, and then within that expression block, you get to do all the nasty things like native pointer dereferences, etc. And also FFI calls. You can't make an FFI call directly. It has to be in an unsafe block. So all these things are basically big warning signs saying, okay, you need to be a little more careful here and make sure that you obey the rules and you don't break any system invariants.
Does it mean that inside an unsafe block, compiler has less to rely on and doesn't apply all the optimizations?
It applies all of the rules for the type. No, it's a distinct two sets of types involved. So native pointers don't look like these reference types here. There's a different syntax for declaring that kind of type. And thus, if you have an unsafe block, you still get all the analyses of things like that the lifetimes of references are being properly used. It's only unsafe pointers that get treated, what's the right word? They're basically ignored by the compiler at that point, trusting the programmer to do it.
So how many of these unsafe blocks did you need to build the Rust compiler?
I don't have that statistic handy, but it'd be easy to grep for. I don't want to take the time to do the grep right now. Maybe you can come to me offline. The answer is there is certainly some, but there's less than there used to be. Like people used to do crazy hacks in the name of efficiency in the compiler, like things where they said, oh, we don't want to deal with reference counting on this data type, so we're going to just allocate it on the heap and just ignore the fact that it's shared and use a native pointer everywhere and just trust that we know how the allocation paths are. So that was something that we used to do, but eventually someone said this is unnecessary. Once this lifetime system, remember I was talking earlier about having a main function with an arena? Basically, someone realized, hey, we can take that arena and these types that we've been doing unsafe stuff with, we can start allocating to an arena that's basically has the same lifetime as the current compilation unit. And then you're assured that the objects you allocate to that arena live as long as the current compilation of that function. And so you have a sound and proven sound approach there. So the number of unsafe blocks has gone down over time, is the short answer, as the language has gotten better. Okay, I think that's everyone, right? All right. So, yeah, so we were talking about, so I've got these read-only borrows, and the crucial thing here is that you have to assume they're aliased, as in, the programmer does and the compiler does, because, maybe they were. And so that means that, for example, down here, this called the try modify, it's an error to do that because you don't know if that vector is aliased by something else. And so it tells you can't borrow this immutably borrowed thing as if it's mutable. And that's a bummer because, I'm a imperative programmer. I want my algorithms. And so this is where the exclusively borrowed mute borrows come in, where now you can do ampersand mute, and then you can call the modified vec, and that works fine. And ends up printing 1, 2, 3, 4 here. So A crucial detail, because a lot of people misunderstand this, I misunderstood it for a really long time. Ampersand mute, it sounds like it means, oh, all mutation must go through this, but that's not actually what it means. Most types that need mutation do want to use this form because most mutation, there's some sort of invariant you're trying to maintain where you need exclusive access to actually properly update that data structure. And so ampersand mute is the right thing for most mutation, but there is plenty of mutation. Like if you just have, for example, a counter on a data structure and there's no like relationship with the other piece of the data structure, there's not a reason to require ampersand mute access just to update that counter. It can be an atomic integer that you use in a compare and swap or atomic increment on. And so that's something where we have various types that don't require ampersand mute access to mutate them. So my opinion, my motto here is that it's not about exclusive access. It's not about mutation. It's about having exclusive access. That's what ampersand mute denotes, and should have perhaps been named something else to make that clearer.
Those special types that you can mutate without requiring the mutable access, are they predefined and supplied by compiler, or you can define a custom one?
There's a mix. So there's predefined ones like atomic word. It's for, that's just the kind of thing where you can't just add new atomic things. You need runtime support, you need processor support for that. But there's also generic types where you can have, there's certain, we can talk about it later, but the point is there are certain cell types that can hold data. One kind is one where it's basically always forces you to take a copy of the value, and if the value isn't copyable, then you're not allowed to even put it in there. And there's another kind of type, a ref cell type, where there's that rule, right, where you have either many readers or exactly one writer, one person with exclusive access. And the cute thing about the ref cell is that it enforces that, but it does it dynamically. It's a library type that's been implemented where it enforces the rule dynamically. And so if you break the rule, you're allowed to, attempt to mutate this thing while there's now saying borrow, and what happens is you get a runtime failure. But a clean one, it shuts down the system cleanly when it does this. It shuts down that thread cleanly. So it's a crucial difference from like a segfault or a data race. That may or may not have answered your question. Okay. So how much time do I have here?
2 minutes left, and actually the audience, you exhausted all of your time. You have 10 seconds left, audience.
Okay. So again, I want to just point out that this exclusive access versus ownership thing, they seem quite similar, and they are pretty similar, but in my opinion, the interesting thing is that ownership is the power to mutate plus the responsibility to actually clean up the resource, while ampersand mute is all the power, for really being able to mutate it, but none of the responsibility. You can't, in fact, it's worse than none of the responsibility. You can't drop it. You can't clean it up. The best you can do is make another one and swap it in, which is legal. Okay, these are demos of like the various ways that ampersand mute, these errors that it checks, but you guys can see the slides yourself. Hopefully some of you took down that tiny URL at the beginning. We have method calls, we have virtual dispatch, and the interesting thing about methods is that there's, again, the three kinds of types where you have methods that just consume the receiver, you have methods that have read access, and you have methods that have exclusive access. The interesting thing about these methods is that the way it works, I don't have time to, I think, get into this in too much detail, but the neat thing, depending on your point of view, is the sugar we have, where method invocations will automatically do the borrows and derefs as necessary. So these calls here to isSum, isNone, and grab.unwrap or, the interface on the top here reflects 3 different kinds of argument passing protocols, but the method calls all look the same. This is a huge boon in terms of programmer convenience. We don't do it for all the other arguments. It's a special thing about the self argument, the one that's the receiver in a method call. But it's a huge reason why you're not just wasting all your time figuring out how many stars or ampersands do I need to put in. You get away with a lot with this rule. Okay, we have smart pointers, but I don't think I have time to talk about them because I only have 30 seconds. Too bad. We talked about lifetime elision. We have generics. The one thing I want to point out here is that we have parametric polymorphism, but it's not, and we have F-bounded polymorphism, so Rust is not C++. We have basically C++ concepts already in the language. We check them at the time you define the trait. So here, this trait, the time that you define the method, this method you can't print this thing or this T because it doesn't have the right interface provided. Uh-oh, you don't have much time for your question. This better be.
What's hash mark test?
Yeah, we have unit testing built into the language. So you annotate an empty function, a function with no arguments as test, and that means that when you compile the compiler or the special mode, it generates a binary that then runs all your unit tests. This is just sort of software engineering awesomeness that just has come up over the years. So the thing I wanted to hopefully get to, I don't know if I actually have time or not. All right, so the thing I wanted to talk about, besides f-bounded polymorphism, is that we have these traits, right, which are like Java interfaces. You explicitly say what method something has, and then you use that as bounds on a type parameter. Okay, that's interesting, but it's sort of old hat. The interesting thing is that that kind of programming doesn't suffice in all cases. This is, in particular, if you have a mix of things on an array, where you have both a rect struct and a circle struct, you can't mix those things into a parametric array where all the types have to be the same. That doesn't work because they need to be the same type all the way through. It has to be uniform. So the crucial thing is you need object-oriented programming, right? You need to be able to actually have virtual dispatch. And the awesome insight that Rust has is it takes the same system that you use for trait bounds, or you use for these, for bounded polymorphism, and it just turns them into objects by saying if you have the way we encode this is by saying if you have a reference to a trait, that basically means that you have a special fat pointer. You have a pointer to the actual data that the actual representation type, and you have a second word that's part of this fat pointer that points to the V table. And this is a really cool way to it's not the same as a class hierarchy that you have. Instead, this is an arbitrary sort of graph structure where the traits can inherit from each other, and you're just passing things around, and the V tables are part of the pointer themselves. So this is really cool. Okay, but this crowd probably doesn't care as much about OOP as well, I don't know, actually. There's a lot of JavaScript people here. Right. I'm thinking curry on, so I'm thinking FP, but okay. Point is, we have closures as well. You don't need a reminder about what closures look like. This is the slide that somebody wanted way long ago. The bar syntax are syntax for closure expressions, and you can define closures. So yeah, that's nice. We're going to skip this. We don't have time. We have RAI. We have destructors. It's just another trait. You implement this trait, and you get a destructor. Boom. There's a simple example, but also the more important thing is this is an example of how our reference this is a simplified version of our reference counting system. So it's just another piece of Rust code that it's a reference, our RC pointer is just something that implements drop to properly maintain the count. Oh, it's such a shame we don't have time. I guess come see me after, because this is a really awesome part, but we didn't get a chance to talk about it all. But also a new condition for safety, which is to be data erase free, which is pretty awesome. And there's a great blog post about this topic called Fearless Concurrency. So yeah, all the stuff that you need to hack on Rust yourself is at this website. So you could all go there right now and download the Rust compiler and start running your computer right now. And of course, you're all doing that, I can see. But perhaps more importantly, the playpen is something that you can get to. I might not be able to get to it, actually. But this is something that you can actually visit and run yourself in the browser. And it goes to a dedicated service online. So these slides, actually, every piece of code that I have on here has links to the playpen. So we're going to see some demos to get you all geared up. These are like 3 little tasty tidbits. So the first thing, zero cost abstraction. We heard Bjorn say that over and over again. It's a huge thing for us, too. But not to compromise safety. That's the first and foremost thing. But still, zero cost abstraction. So this is some pretty high level code. Oh, this is very bad. How do I get back? Sorry, I'm using a hacked version of my Chrome for Mozilla, so it doesn't show up for Firefox. It doesn't show the URL bar, but unfortunately, it doesn't show the URL bar ever. So we need a presentation mode. So anyway. This is an example of fork join concurrency. So this is really slick because we have some data that's owned by the local stack frame. namely or somebody. It's owned by somebody. It's not owned by the local stack thread. It's something we have borrowed. But the point is that we can split the input array into 4 chunks, hand them off to threads, and have them process those things concurrently. And then, but just passing off pointers. We're not making copies of the data. And then we like do our processing and get a result back. Of course, you wouldn't typically do this for something like Max. That's kind of stupid, but this is just illustrative. There is a caveat, which maybe we'll get to. We'll see. So, okay, but why Rust? Why, in particular, why is Mozilla doing this? And the simple answer is because it's the only way you try to modify a collection while you're iterating over it. Rust doesn't have this. So, in particular, this example is one where in C++, if you try to modify a vector while you're iterating over it, that's a bug. As in, it might reallocate the backing store for the vector, but the iterator doesn't know that. And so you've just invalidated the iterator, but it doesn't detect that, and so you just get garbage. But we detect it and tell you at statically compile time, no, not allowed. And here's why. Yep.
When you said you optimize the iterators, does the compiler know about the iterator to optimize it?
No, that's something that's the iterator constructs a library, so there is some special code in there where the iterator is itself taking advantage. There's a tight coupling between the vector representation and the iterator that it yields when you ask for it.
Great, thanks.
Okay, and finally, the other point I wanted to make was about concurrency. I'm trying to like get to a lot of slides here. Oh no. Oh, okay, that makes sense actually. I tried to get to something that I couldn't get to. Oh no. Okay, so yeah, let's talk about Rust and what it is and why we're making it. So it's a new systems programming language. Actually, so much of my talk, I wish I had the time to revise it entirely based on Bjarne's, because so much overlap was there. So we need to have fast code for systems programming, and we want to have a good FFI interface to interface with native services. You want to have low-level control, things like data layout. But also, we've got decades of PL knowledge to draw upon. So we want to mix in all these classic ideas, drawing from the best-of-breed stuff, stuff from C++ like RAII, but also things from the ML and Haskell and et cetera communities with generics and F-bounded polymorphism, et cetera, pattern matching, all that great stuff. But perhaps most importantly, the most exciting thing about Rust is the focus on safety. And that for us means not just being memory safe in terms of no seg faults, no pointer dereferences, or garbage pointer dereference here, where we're doing some iteration over an input vector, and we're doing a filter as we go, and then summing. And this compiles into this assembly code. This is really tight assembly code considering how relatively high level that code was. And in fact, if you want to get even more high level, you could have written the code like this, and it compiles into the same assembly code. And this is due to a mix of stuff between both relying on LLVM to do great optimizations, but also, question? That's a closure. That's our syntax for closures, which we may or may not get to in this talk. We'll find out. But that's our syntax for, lambda expression is the I within the bars. So, yeah. But it's not just LLVM that we're relying on here. It's also that the iterator abstraction we use allows us to do things like not have bounds checks during the actual iteration itself. But also, we have memory safety. And this is an example I like because this isn't an example that everyone necessarily thinks of. In particular, this is a bug that plagues even safe languages like Java. Namely, you may have heard of concurrent modification exception.